Hello. This lecture will cover pages 50 through 55 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on loop analysis, Chapter 3C, Understanding Loop Analysis. We're going to start out by looking at page 50, a loop, sometimes referred to as mesh analysis. A loop analysis is a technique used to solve a particular circuit problem. Note, as we go through this, you'll see that loop or mesh analysis uses Kirchhoff's voltage law to calculate loop currents. And I want you to compare that to what nodal analysis did back on page 44. Note, nodal analysis uses Kirchhoff's current law to calculate node voltages. I want you to think about that when you read it, because I want you to understand nodal analysis uses Kirchhoff's current law to calculate node voltages, and I want you to read this and understand what loop analysis does, and you'll see it as we work through the problems. The procedure when using loop analysis to solve a problem is this procedure. We're not going to go through it because you're going to take out this page 50 and have it handy as we go through the next 10 problems or 8 problems. We have 4 problems to go through in this lecture, and we do some more problems in the next lecture. But I want you to just follow through, because this is the procedure that I'm going to use, and it's very important you understand it. Starting out on page 51, example number 1. For the circuit shown below, solve for the loop currents I1 and I2 using loop analysis procedure discussed on the previous page. Here's a circuit, and for this first example, I'm going to assign some currents. I assigned a loop current in a clockwise direction around loop number the left-sided window, and I went ahead and assigned a loop current in a clockwise direction I2 around the right-sided window after I chose my reference node. 2 loops, so we'll need 2 equations unless you have dependent sources. All dependent sources do are add additional equations for the controlling variable. That's nothing new when we get to that point in loop analysis. I want you to notice here that these currents have to take into account all the elements in the circuit. And what I mean by that is I could have made loop 1 this loop like I've done, and loop 2 could have started here where loop 1 starts, and it could have went around this direction and took the whole outside loop. And if you looked, we would have picked up every single element with those 2 loops. You do not have to assign the 2 loops the way I've done here. You could have went loop 1 the way I assigned. Loop 2 could have been this outer loop. We'll get to that later. But this is the way I chose to do the loops. Around loop 1 by Kirchhoff's voltage law, you have a plus 5. Starting here, you have a plus 5 minus 1 times I1. This is a technique I want you to use. When you see a resistor and you're doing loop analysis, you say minus the resistance value, and then you stop and think what current goes through that resistor. So in this case, you say minus 1 right away, or minus 1K, or minus 10K, whatever it is. Minus 1, then you stop. What is the current? It's I1. Then you're down here. Minus 6, right away. Minus 6. Then you stop and think, what current goes through there? The lead current is I1. There's your plus to minus for I1. And then you subtract I2 because it's in an opposite direction with the parentheses. Minus 10 equals 0. You clean it up, and there's your first system equation. Let's go around loop number 2, starting down here. Plus 10, minus 6, and then you stop and think. What current goes through that? The lead current, plus to minus, is I2, because you're in loop 2, minus I1, because it's in the opposite direction of I2 if you take a look. They're both clockwise. Then you're over here. Minus 2, and then you stop and think. What current? The only current there is I2. Equals 0. You clean it up, you get your 2 system equations. What I've done here, use determinant analysis. We're using Kramer's rule, they call it, and I got a coefficient determinant. These coefficients form a coefficient determinant, and I solve it for 20. If you look on the next page, you already probably know this math technique. I1 you take the coefficient determinant and you just substitute in the constants on the right-hand side of the equation, right here, for the coefficients of I1. And you divide by the coefficient determinant. You get 1 amp. Same thing for I2, except you're substituting in those constants for the coefficient of I2. Divided by the coefficient determinant, you get 2 amps. I1 was positive 1 amp. It went in the clockwise direction. If it was the opposite direction, you got a minus there. I2 also, the clockwise direction was correct. It's 2 amperes. Since I2 is greater than I1 in our analysis, the current through the middle resistor is 2 minus 1 is 1 amp in the direction of I2. I2 is larger. So we have 1 amp here flowing in this direction from here to here. Therefore, my solutions, I1 is equal to 1 amp in a clockwise direction, I2 is 2 amps in a clockwise direction, and I 6 ohm, I1 is 1 amp, I2 is 2 amps, I6 is ohms is the 1 amp going up. So now you know the currents, you can calculate resistance, you can calculate powers, voltages anywhere else in the circuit. I asked you 4 or 5 questions right here. What is the power P, the power in the 1 ohm resistor? What's the power in the 2 ohm resistor, and so forth? Make sure you can see how I get these. I'm just using, in these cases here, I'm using I squared R because their power is absorbed, the resistance values. Down here I know the voltage and the current. You don't know the resistance for these power supplies. So it's the voltage times the current. You get 5 watts in the 5 volt. It's supplied because of the direction of current entering the positive node, the negative terminal. Remember that? And down here the power in the 10 volt was 10 watts, and it's supplied because the current direction is entering the negative terminal there also. A quick check before you move on is, did the sum of the power supplied equal the sum of the power absorbed? If they do, and they do, you know you got the problem right. The next example with loop 2, or example 2, loop mesh analysis for the circuit shown below. Solve for loop currents I1, I2, and I3 using loop analysis procedure. Then find the current in the 3K ohm resistor and the current and the power in the 3K ohm resistor. So here's my windows. I chose loop I1, plus the minus here, plus the minus there, I2 down here, plus the minus here, plus the minus here, and I3 over here, plus the minus there, plus the minus there, because it's the lead current, and plus the minus there. 3 loops, so we need 3 equations. There's my reference node. The loops include all the elements, so we're good to go. Let's just do the first equation. Around loop 1 by Kirchhoff's voltage law. You start right here. The first thing you see is a resistor. You say minus 4K, and you stop and think. What current goes through that? I1. Just I1 goes through there. You come down to here, minus 6K. You stop and think. What's the current that goes through there? The lead current's I1 minus I3. Minus 6 equals 0. You clean it up, there's your first system equation. Stop the video and get a piece of paper and see if you can go around loop 2 and clean it up, and loop 3 and clean it up using my technique, and see if you get these 2 equations. There's your 3 system equations that describe that network. You have to do this very carefully, and you have to check your work, because it's very easy to make a mistake, obviously. Not so much using Kirchhoff's voltage law. I mean, it's cleaning this up algebraically to get this, and cleaning this up algebraically to get that, and cleaning this up to get this. I use matrix analysis here to solve for the currents I1, I2, and I3. You can use whatever technique you want once you have the system equations. There's the currents. Notice some of them go in a counterclockwise direction. What would be the current and power dissipated in that 3K ohm resistor? I want to know what the power dissipated is in this resistor. Well, you have to take a look to see which current is larger, and it wins the direction, and the other one's in the opposite direction. So if I noticed that. If you look at the circuit, and you can see that the current through the 3K ohm resistors, I2 minus I3, is 595 microamps. So the power is I squared R. The power is 1.06 milliwatts. The power in that resistor is 1.06 milliwatts. And then finally, loop number 3. For the circuit shown, example number 3, using loop or mesh analysis. For the circuit shown below, you write the 3 loop equations in standard form that describe the network. Then solve the loop currents I1, I2, and I3 using simultaneous equation program on your calculator or an app on your smartphone. Note, this problem, you should be able to work this in less than 10 minutes. That's where you have to be. You have to make sure you can solve simultaneous equations on your calculator or on an application in your smart device, because you don't have time to go through the techniques that you learned in math. Write the 3 loop equations for I1, I2, and I3. There's the 3 loop equations in standard form. Make sure you can get them using the techniques I've shown to you. I1, I2, and I3. Now you could find any current, voltage, or power for any element in that circuit. Loop analysis is very easy to do once you understand the convention here. We're going to see learning assessments in the textbook. Look over 2 more examples just to make sure you understand this. E313 and E314. Let's see here if I have them handy. Yeah, right here's the 2 problems. I think you can see that okay. First problem here, it says use mesh or loop analysis to find V out here. I get a reference node. Look at your procedure. Get a reference node right there. There's your ground. I'd make this loop I1, make this loop I2. Write your system equations, get them in a standard form, solve them, and whatever I2 turns out to be, you take I2 times the 6K, and that gives you the voltage across this resistor. That's all there is to that. Make sure you get the answer. Make sure you can get that answer there. I don't know why they keep it as a fraction. Obviously it's 6 point something volts. And down here, another example. Assign your loops. Doesn't make any difference if this is I1, this is I1, this is I1, but I made this I1, we'll say, make this I2, make this I3. Use Kirchhoff's voltage law to write your system equations, clean them up, and solve for I1, I2, and I3. And then if you take a look, they want you to find V out. Well, the only current that's going to go through that is I3. You take I3 times the 6K and you give you V out just like you did up here, and you should get 8.96 volts for that one. The techniques of using either nodal analysis or loop analysis requires a little bit of thought, that's all. What I want you to do when you see a problem on an exam or on a quiz or in the future is I want you to look at it for just a minute before you start working it out. And then decide, when you reach into your toolbox, what tool do you want to take out and use? Do you want to use nodal analysis or do you want to use loop analysis? Because you'll find out that sometimes nodal analysis is a lot easier than loop analysis on a particular problem. But on the other hand, in other problems, the loop analysis may be advantageous over the nodal analysis. It's up to you to just take a minute before you start working that problem on the exam to choose a tool. Now, in this next exam coming up, I'm going to tell you this problem you have to use nodal analysis, and in this problem you have to use loop analysis. But after we get through this chapter, you can use whatever tool you find more appropriate and easier to solve the problem. That concludes this lecture.